In this video we present ACE, the Autonomous City Explorer. This mobile autonomous robot was developed as part of a 1.5-year project at the Institute of Automatic Control Engineering, Technical University of Munich, Germany. The goal of the ACE project was to create a robot that is capable of finding a designated goal location in an unknown urban environment. The robot consists of a differential wheel mobile platform, 2 laser rangefinders, a touchscreen, a loudspeaker, and a multifocal camera head. The robot was supposed to find its way from the campus of the Technical University of Munich to Marienplatz, the central square of Munich. ACE was given neither a GPS sensor nor map knowledge of the city. It was only allowed to retrieve information through interaction with passers-by. In the following, we will explain some of the hardware and software solutions developed to overcome the challenges of navigation, perception, and interaction in unknown urban environments. To localize itself, ACE uses odometry. In essence, it measures the revolution of its wheels. However, even on very smooth ground, wheels tend to slip and skid from time to time, which means that there is a growing error between the measured and the traveled distance. To overcome this problem, ACE makes use of a laser rangefinder. This sensor measures the distance in the horizontal plane to objects in the environment. By analyzing the shift of object positions in consecutive range measurements, ACE concludes whether it has actually traveled the measured distance and can thus correct the odometry error. To avoid falling down the sidewalk or other negative obstacles, ACE uses a downward-looking laser rangefinder to assess the traversability of the terrain in front of it. The information from this laser is fused with the occupancy grid used for navigation. Using particle filter-based SLAM, the robot builds a 30 by 30 meter occupancy grid of its surroundings. In this grid, it employs a dual path planning strategy, using both a bounding box-based visibility graph planner for open spaces and a Voronoi-based visibility graph planner for narrow passages. To retrieve information about global waypoints, ACE needs to ask pedestrians. It recognizes humans in its vicinity by searching for patterns of human faces in the camera images. Once it has detected a face, ACE approaches the pedestrian and initiates an interaction.
Hello, my name is Ace.
During interaction, ACE asks people to point the way to Marienplatz. As the robot makes use of multiple cameras, every point in the 2-dimensional camera image is assigned a distance in the 3rd dimension. Once it has extracted such a 3-dimensional point cloud, ACE attempts to fit the model of a simplified human skeleton into the set of points. It uses the pose of this skeleton to conclude in which direction the human is pointing. Humans provide further route information through buttons on a touchscreen. Internally, ACE creates a semantic graph that represents its knowledge about the route. As it makes progress, it associates the graph with the metric occupancy grid and sends the next node to the path planning module as a global waypoint. For safety reasons, ACE cannot simply cross streets, but must stop at intersections and wait. It recognizes intersections by searching for patterns of traffic signs and traffic lights. The robot was trained with about 10,000 example images of traffic signs and lights to learn an abstract representation of the desired patterns. When crossing intersections, ACE has to follow a human for safety reasons. It does so by tracking a t-shirt with a chessboard pattern on it. On August 31st, 2008, ACE successfully completed its mission, navigating a distance of 1.5 kilometers in approximately 5 hours and interacting with 38 passers-by.
Thank you very much for your help.
Further information can be found at www.ace-robot.de.